Hi everyone, welcome back to a new week and a new architecture. So this week we will talk about recurrent neural networks. And since recurrent neural networks is kind of a tongue twister, at least for me, let me just say RNNs for short. So RNNs are neural networks that work with sequence data and especially text data. So right now RNNs are usually used for text classification, classifying text into different topics, but also language translation or sentiment analysis and even generating new text. And since we have sequence data, there is a time component now in the network where the network not only looks at a given input at a certain time point, but also all the previous inputs from the previous time steps. And in order to make that work, we have to make a small adjustment to our backpropagation algorithm. This is called backpropagation through time. It's actually a very simple modification, and we will learn all about that today. And since we can have usually longer sequences, we encounter again the vanishing gradient problem. So in previous lectures, we had a vanishing gradient problems if we had a very deep network with multiple layers. Here, the vanishing gradient problem comes from the fact that we can have long sequences. So in order to deal with that, there's at least one approach that is commonly used. It's the long short-term memory, LSTM. There are many other approaches, but this is still one of the most popular ones. And we will also talk about using LSTMs for reducing the vanishing gradient problem. And then, if there's time left, we will briefly talk about attention mechanisms for RNNs. So attention mechanisms are very popular right now in so-called transformer models, which are a new type of architecture, which we will not cover in detail in this course, but the attention mechanism originated from RNNs. So that is also something interesting to talk about. Originally also I planned to have a two-series lecture on RNNs, but I just noticed that we only have 3 lectures in total now left in the semester. So one will be RNNs, and then I really also wanted to introduce autoencoders to you, which I will do next lecture, and then also generative adversarial networks in 2 lectures. So because many of you wanted to learn about generative models, so I will try to keep this RNN short, this RNN section. And so let me not waste too much time on the introduction again, and let's get started. Like always, all the slides are available on GitHub if you would like to download them for note-taking. And before I start talking about RNNs, let me go back a few hundred years and talk about a classic technique that people used for text classification. So this classic technique is called, or is based on the back of words model. And I'm just showing you this here because it will be relevant to RNNs. It will kind of illustrate why RNNs are useful. So in this approach, in this classic approach, what we did is the following. So let me go through this step by step. Let me label this as step 1. So we obtain a raw training data set. So again, the goal is classification. We want to classify, let's say, whether a text is positive or negative, or any type of class label, could be a document category. So let's assume we have a classification task, and I have collected my raw data set. In this case, I have 3 data points, 1, 2, and 3. And each training example here is, just for simplicity, one single sentence. So there's one sentence here in the first training example, a sentence here in the second one, and a longer sentence for the third one. It's of course just a very simple toy example. So the first step in the classic approach is to build a vocabulary. For building the vocabulary, I look at the whole training data set, I look at this whole data set, and simply list the unique words I can find there. So it's just a set of unique words, this vocabulary. And then I can give each word an index so that I have a fixed position for each word. So again, when you build the vocabulary, the ordering of the words doesn't matter. It's arbitrary. But then we use the vocabulary to create vectors. And for this, we want to be consistent with the position. So we can assign an index position to each word here. So this is the index position from 0 to 8. So I have 9 words in this vocabulary. You can think of it as a Python vocabulary dictionary, by the way. Once I have this vocabulary, what I'm going to do then is I'm building my real training set, so my design matrix style training set. This is the design matrix we worked on in the very beginning when we worked with multi-layer perceptrons, logistic regression, and so forth. where the number of rows here, n, is the number of training examples. So the training examples are the rows, and the columns here, let's say we have m columns, are our features. So each feature is constructed, or the features are constructed from the vocabulary. So if you would count, let's say 1, 2, 3, 4, 5, 6, 7, 8, 9. These are the 9 values I have in the vocabulary. So let me use the actual index positions. So this is the index position 0, 1, 2, 3, 4, 5, 6, 7, 8. And what I'm doing now is I'm looking up for each index position what word it is. For example, for the first one, it's and then for each training example, I look how often the word occurs in the training example. So if I take my first training example, this one here, this corresponds to this one here. I look, okay, does this training example contain the word and? No, it doesn't, so I put a 0 here. Does it contain the word is? So it's my second entry. Does it contain is? Yes, it does. It contains is, so I put a 1 here. Next, I look at the word one. One, is it in this training example here? No, it is not, so I put a 0 here, and I continue this for the whole vocabulary. And then just as an example for the second, or let's take the third training example, because it's maybe more interesting, there are more words in there. So let me take this one here. Now again, I do the same game basically. So I look at the first entry in the vocabulary. Does the text contain and? Yes, it does contain and. So it contains and here and here. So I have 2 times and. So I put a 2 here and so forth. So I just built this design matrix by counting how often each word occurs in the data set. And the positions are based on the vocabulary. So this is now a matrix that contains the word counts. And we can also use term frequencies, normalized word counts, and so forth. That doesn't really matter here. I'm just trying to explain a classic approach. And the problem with that approach, though, is that each position is independent. So there is no ordering. We don't keep the order from the original text. So since the order in the vocabulary is arbitrary, we don't really maintain the structure from the text. And this has limited power, because sentence data is, you can think of it as a type of sequential data. So we lose the information about the sequence of words if we use such a model. But also, let me just finish this example. So now we created this design matrix. We would use that then, like in a normal classic way, to train the model. We have then usually some class labels, just calling them 0 and 1 for simplicity. So 0 for the first training example, 1 for the second one, and 0 again for the third one. And then I'm using this as input for training a classifier, such as, for example, the multi-lab receptor we talked about earlier, or logistic regression. But again, the problem with that approach is that we don't really maintain the sentence structure. So here we may lose valuable information, because, for example, if I have a sentence like Mary has a cat, or it doesn't really make sense, but a cat has Mary. So it doesn't really make sense, the second sentence, but in both cases, this would create the same vector, the same back of words embedding, although the sentence has a totally different meaning. So a model like the multi-lab perceptron or logistic regression, which is based on this design matrix, is not super powerful. We lose information. And in this lecture, we will talk about the RNNs that are better at modeling such sequence data. By the way, one model we have already seen that is capable of handling such sequential text data would be the convolutional neural networks that we talked about last lecture. In the last lecture, we talked about the CNNs in the context of image classification. So we had the 2D CNNs before. But if we just use convolutions in a single dimension, for example, like in this text data set, we can also use them for capturing the sequential relationship between text. So we could have a kernel that slides only in one direction, only down, where the kernel, for example, captures the word the, and then the next part it would actually capture this white space here, and then it would slide further down and so forth. Yeah, convolutional networks can be used. They have been used for text. It's just like they are not as powerful as the RNNs. They can be useful though, and we will not talk in more detail about this now though, because the main topic of this lecture is really RNNs. And if we also would talk about CNNs for 1D text classification, we wouldn't get done with the RNN lecture. So the reason really why we talk about RNNs, it's because it's the topic of this lecture. But I'm just saying you can also use 1D CNNs for text classification if you like to. Okay, the lecture overview for today. So first of all, I will introduce RNNs now that I have mentioned it a couple of times. Then we will look at the modification of backpropagation that we can use for RNNs. This is the backpropagation through time. Then we look at certain modification of RNN architectures themselves by using the so-called long short-term memory, which makes them more robust to vanishing gradient problems. Then we look at how we can use RNNs for text classification. I will mainly show you or give you links to coding examples where you can use RNNs to classify texts. And then we will look at a generative model where we use RNNs, so-called character RNNs, to generate new text. For example, by training an RNN to read a book and then generating new text that is very similar to the book. And lastly, if there's some time left, I will briefly show you the attention mechanism for RNNs, and then also talk about transformers, which are architectures that are very popular nowadays for text classification, and they just use attention mechanisms without RNNs, and they are very powerful. However, also in the interest of time, because next lecture I wanted to talk about autoencoders and generative adversarial networks, we will not go into much detail here. Just wanted to show you that there's a relationship, so that the attention mechanism was originally developed for RNNs, and now it's really used standalone in transformers, and it's also very successful for text classification. So in the models we talk about in this lecture, they are not only good for text analysis, but also all kinds of sequential data, where sequential data is typically not IID. IID in machine learning stands for independent and identically distributed. So here they are not IID because one training example, or in sequential data, one training example may depend on a previous training example where we have a time dimension. So models we talk about in this lecture can deal with that time dimension. And other applications of sequential data may include also speech recognition, for example, modeling acoustic data in general, or even songs, audio examples, and music. Language translation, which is a little bit different from text classification, because in language translation we take one sequence and convert it into another sequence. Or stock market predictions. These would also be an example of time series data where we have observations for certain timestamps. And DNA and amino acid sequences. So amino acid sequences, amino acids are the building blocks of proteins, and they can be also written as a sequence. They are similar to text data because we have letters here. In this case, in case of amino acids, we have 20 different letters. In case of DNA, we only have 4 different letters, but they are very similar to text data. Okay, let us now look at RNNs, how they can deal with that sequential nature of the data. So on the left-hand side, I'm showing you the classic approach, for example, a multi-layer perceptron, where we have some input X, then a hidden layer, if we have only one hidden layer, and then some output Y. In the recurrent neural network, RNN, we have an input. I added a time dimension here, T. Also a hidden layer and an output. But again, now the new part is that we have this T here. So we have labeled the time step. And what makes the recurrent neural network recurrent is this recurrent edge here. So there's some loop or recurrency. It's a little bit hard to understand RNNs this way. So let me unfold the RNN. So here I'm showing you again the RNN from the previous slide, a single layer RNN, and I'm unfolding this recurrent edge here. And how that looks like is, for time dimension t, I have something that just looks like a multilayer perceptron. So this looks like a multilayer perceptron, but what is new is that it receives two inputs. So at this time step t, it receives the input from x, so the data input, but also it receives an input from the previous hidden layer or from the previous time step. So RNNs, in contrast to MLPs, receive two inputs for the hidden layer: the previous hidden layer state and the data input. That is the time component here. So this is a single layer RNN because we only have one hidden layer, but of course we can also extend this concept and have multiple hidden layers. So at the bottom here, I'm showing you a multi-layer RNN where we have two hidden layers. This would be the first hidden layer, and then this one would be the second hidden layer. There are actually several different types of sequence modeling tasks. So here's an overview of the 4 most common types, and this slide is inspired by a really great article by Andrei Karpathy, which I really recommend checking out this article. So the sequence modeling task I showed you in the previous slide was this many-to-many sequence modeling task, where we had one output for each input. So we had these input-output pairs. So in the other tasks, it works a little bit differently, and let me go through them step by step so it's not so overwhelming to see all of them at once in the same slide. So the simplest one would be the many-to-one sequence modeling task. This is the task I mentioned to you in the very beginning, where we talked about text classification. For example, you can think of it as sentiment analysis. You want to analyze whether a tweet on Twitter is positive or negative, for example, having positive opinion or negative opinion about a topic. Or you can think of it as movie classification. So is this movie review a good or bad movie review? So the inputs would be all the sentences in the movie review, and the output would be whether it's a good or bad movie based on a review that we read. That would be a simple case of a many-to-one. The many comes from the fact that we have many inputs, so all the sentences, but only one output, the class label. Another task is the one-to-many task. Here we only have one input and we have multiple outputs. For example, one example of this could be image captioning, where we have an image and we ask a neural network to describe what is in the image. Here the network would create the sequence from the image by describing it, but there would only be one input, which is the image itself. Another task is the many-to-many task. Here we have multiple inputs and also multiple outputs. So like I said before, in this case, we have a pair of inputs and outputs. So this would be a common task, for example, for video captioning also, where we describe a sequence of images via text. So extending from the example I told you in the previous slide, where we had one image and we create the sequence of text. Here we can think of it maybe as a video where we see multiple pictures and we get multiple outputs here. Another example of many-to-many would be this one here, where we have a shift. So we observe the inputs first and then we generate the outputs. And one common task for this one would be language translation. So it wouldn't make really sense to translate a sentence step by step, word by word, because that's usually when nonsense translations happen. So if you would literally translate one by one, word for word, from one language in the other language. So what you need to do in order to translate a language or a sentence is to read the whole sentence first, then comprehending it, and after reading the sentence, you generate the translated sentence. So this would be an example of this many-to-many shown here on the right. But to explain some of the main concepts behind RNNs, let us stick a little bit longer with a many-to-many sequence modeling task, where we have the input-output pairs, the one-to-one pairs at each time step, so these pairs here. You can also think of the many-to-one sequence modeling task, by the way, as a special case of this many-to-many sequence modeling task. For the many-to-one sequence modeling task, you would simply ignore these intermediate time steps. You would only have one output, and this output would not be only depending on this input, but it would be the output for all the inputs. But let me not clutter up this slide too much, because all I wanted to say is really the core concept behind RNNs is that for each hidden unit here, the RNN receives 2 inputs. And using this basic concept, let's now see how we can adjust backpropagation to work with such a time dependency. So the time dependency in RNNs is modeled by a concept called backpropagation through time. And in the next couple of slides, we will look at how this backpropagation through time works with the many-to-many architecture. Just like in a multilayer perceptron, we have a forward and a backward pass. In the forward pass, we compute the predictions, the outputs, and then in the backward pass, we compute the loss and backpropagate the errors to update the weights. And here, in particular, we compute the gradients of the loss with respect to the weights, which we update. So here I'm showing you again a compact version of the RNN, and on the right hand side I'm showing you an unfolded version. But let us talk about the left hand side first, and what we are going to do now is we talk about the forward pass first before we do the backward pass, because then it will be easier to understand how backpropagation through time works. So in the forward pass, or in general, in the forward pass, we use weight matrices, like in a multilayer perceptron. And here I'm showing you where the weight matrices are. So you can also think of this substructure here, just like as a multilayer perceptron, and a multilayer perceptron in particular with one hidden layer. So this weight matrix is connecting the inputs to the hidden layer. And we usually call that also the hidden layer, because it's computing the net inputs for the hidden layer, and then we apply an activation function to compute the activations of the hidden layer. I'm not showing you the activation functions in this slide here though, for simplicity. I will show it to you in the next slide. So then we have a second weight matrix here, and that is the output layer, which is computing the output from the hidden activations. So yeah, this is the multilayer perceptron part, but then what makes it an RNN is this recurrent edge, and in this recurrent edge we have another weight matrix, and this weight matrix is used for the previous hidden state. So because it's maybe a little bit complicated to look at this in the context of this recurrent edge, let us unfold this representation so that we unfold the time dimension. It's easier to understand then. And what we can see here is, again, the hidden layer and the output layer. And notice that we reuse the same weight matrix at each time step. And then we have this WHH here as another weight, and this weight matrix is multiplied with the activation units of the previous hidden state. So we have matrix multiplication between these. This is really what makes the RNN different from a multilayer perceptron, this time dimension. So there's some more parameters in this network, because now we have this WHH. What I mean is there are more parameters compared to a regular multilayer perceptron. And sometimes also for, I would say, efficiency, I just included it here, we summarize these two weight matrices just by writing WH, and this is just concatenating these two weight matrices. It's usually a little bit simpler to write, so we just write H, and this is WH is summarizing two weight matrices. It's just concatenating them. It's just a convention to use, just showing it to you here. So here I'm now showing you how the net inputs are computed. I kind of hinted at this already in the previous slide, but just to make it clear, absolutely clear, is I included the equation here, and this is computing the net input ZH for time step t. So this would be the net input for this hidden layer, and this is just like for a multi-layer perceptron, computed by multiplying the weight matrix between the inputs and the hidden layer to produce the net inputs. And then we also have a bias unit. So if we would only take these two, this would be just like a multi-layer perceptron, but what's new is that we have the input from the previous hidden activation, which would be this part here. And then to compute the activation of this hidden layer, so this is the net input, we apply a nonlinear activation function just like before. And this could be whatever activation function you learned about. It could be a sigmoid, a logistic sigmoid, or 10H. So it could be logistic or 10H, or relu would be another function to use, any nonlinear activation function that you may have already seen in the previous lecture material. Now, what about the other weight matrix? So here I just moved things a little bit more to the left, so that is what I've shown you on the previous slide. Now let's focus in on this part, computing the outputs using the other weight matrix. And this is just like with the multi-layer perceptron. We have this weight matrix connecting hidden layer with the output, so the output layer, if you will. And then also again a bias unit, and then we compute the net input, or we usually also call the net inputs of the last layer the logits. We compute these, and then we apply again a activation function. And usually in classification this would be our softmax function. And that's it for how we do the forward pass in an RNN. Let's look at the backpropagation through time now. Just like with a regular multilayer perceptron, we have to compute the loss for backpropagation, because what we want to do is we want to update the weights based on the gradient of the loss with respect to the weights. So we want to update the weights such that we minimize the loss. And the loss, it can be any loss depending on what you're working on. But if you have here binary outputs, let's say zeros and ones as class labels, then you would use the binary cross entropy, for example, or negative log likelihood. Or if you have multiple possibilities as outputs, more than 2, then you can use the multi-category cross entropy. In any case, to compute the overall loss for this sequence, you simply sum over the individual losses for each time step. So at each time step you compute a loss based on the class label, the true class label, and the predicted class label. So here it's a bit confusing. I should have maybe used y hat. These are all the predicted class labels, and you would compute the loss between the predicted class label and the true class label, right? And for the whole sequence you would sum over them. And by the way, this backpropagation through time is based, the concept is based on a paper by Paul Verbos, which was published in 1990. It's a long time ago, but it's still very influential, like the original backpropagation paper, because that is still how we do backpropagation in RNNs. And like I said, yeah, the loss is computed as the sum over all the individual time steps that come before it. So for a given loss, let's say time step t, the last time step, we would sum over all the previous time steps starting at the first time step. Expand this concept a little bit to see how backpropagation through time works. So also I should say you don't have to understand every little detail here. It's mostly the same as for the multilayer perceptron, and I'm not going to ask you any tricky questions in the final exam to compute some gradients by hand using backpropagation through time. So there's only one main concept I really want to explain here. So what I'm showing you here is that we want to update the weight matrix WHH, for example, this one here. And in order to update this weight matrix, we compute the derivative of the loss with respect to this weight. And again, we, like in a multilayer perceptron, we use the chain rule mainly for that. So this would be summarized as time step t. It's this part here. And so this would be just one regular thing that we would compute in a multilayer perceptron as well. What's new here, though, is that we have this summation term where we sum over all the previous time steps. So the part that I'm circling here, this could be also summarized as like this, right? And inside, so I'm just using the chain rule to expand this term into 2 terms. And right now I'm summing over all the previous time steps because they are used to compute the current hidden activation, the previous time steps. And there's one particular one I just want to highlight because, like I said, I won't ask you any tricky questions to do backpropagation through time by hand. And really the most important part to understand here is computing computing this one, because there's a problem with that. So here, when we use the chain rule, what we do is we consider all the previous time steps, right? Because at the current time step, if I have h t plus 1, I have to also consider the previous time steps, because they are used together with a weight to compute this current time step. And then again, I use the weight matrix WHH multiple times, and each time I get this hidden activation, and the hidden activation is fed forward here. So in order to compute this term, so the derivative of partial derivative of ht with respect to the previous ones, I apply the chain rule, which becomes a product, right? So I have the product of all these terms here, and depending on how long my sequence is, I may have a lot of multiplications here, 10, 20, depending on how long my sequence is. And like you remember from the multi-layer perceptron, when we had multiple hidden layers, many hidden layers, there was one particular problem, or actually two types of problems. One was the vanishing gradient problem, and one was the exploding gradient problem. That happens if we multiply something multiple times. Today, in the interest of time, I won't walk through this in more detail, through the derivation of this, like I did with the multi-layer perceptron. However, if you are interested, you can look at this nice resource here, which is a little bit more accessible, I would say, than the original research paper by Paul Verbos. So if you want to learn more about backpropagation through time and how to derive it, you can take a look at this article, which is really nice. So let's look now at a technique that helps training RNNs, because like I said before, we have this vanishing and exploding gradient problems due to the product that we use when we compute the backpropagation through time. In particular, vanishing gradients are more of a problem depending on what activation function we use, as you remember from the multi-layer perceptron lectures when we talked about multi-layer perceptrons with multiple hidden layers. Here, there are three different techniques. So the first one would be more addressing the exploding gradient problem, but in RNNs it's usually more like the vanishing gradient problem that bothers us. So what we can do is, the first method would be gradient clipping. That simply means that we set a max value for the gradients, and if the gradients are larger than that, we just prune the gradients. We make them smaller by just setting a maximum threshold. So for example, it could be, you can say the gradients can never be greater than 1.1 or something like that. But yeah, again, this only addresses the exploding gradient problem. It doesn't really help us with the vanishing gradient problem that we mostly have in RNNs. One technique that is somewhat useful is truncated backpropagation through time. So in this truncated backpropagation through time, what we do is we limit the number of steps we can backpropagate. So if our sequence has, for example, 100 elements or steps, we may only backpropagate through 20 or 10 steps. So by that we avoid too many multiplications. So we avoid having too much vanishing of the gradient. So this is a technique that works. However, there's one better technique for RNNs, and this is called long short-term memory. And this was first proposed by Sepp Hochreiter and Jürgen Schmidhuber in the 1997 paper, long short-term memory. And we will talk now about this LSTM mechanism in more detail. Let's take a look at such a long short-term memory cell. I know what you might be thinking. It looks super complicated at first, but I think we can make it easier by walking through it step by step. So the first step is providing you with some context here. So in the upper left corner, I'm showing you the many-to-many sequence modeling task with a multi-layer RNN that I showed you before. And the LSTM now, it takes the place of the regular hidden layer. So we still call this whole thing, let's say, hidden layer. I mean, it's an LSTM now, but it is sitting right here for the current time step t. And it receives as input the activations from the previous time step, like before. So drawing the connection here. So, and that is like before, and also it outputs its activation to the next time step. So in green here, I'm showing you this one. So I'm just connecting them here to show you where it sits in the architecture. And then also it is providing, of course, the output to the next layer, or it could be also directly the output layer. So it is just this pink one here. And yeah, this is the basic context for the LSTM in the RNN. Now, why do we need it, or what is new about it? So one thing to notice here is this cell state. We have now a cell state that we carry through the network. So here in the regular RNN, we don't have a cell state, we only have a hidden layer activation, and that goes, or the network receives the previous hidden layer activation and then it goes to the next hidden layer activation. Now there's also an additional cell state that gets carried through from time step to time step. And here, like I said before, this is the activation from the previous time step and that's the activation from the next time step. But again, in addition, we have these cell states. Also to note are these different operators here in this figure. So there's one type of operator, the element-wise multiplication operator that we have here in multiple parts of the LSTM cell. And there's one element-wise addition operator. And here these sigmas stand for the logistic sigmoid activation function, and we also have a 10H sigmoid activation function. Now there are also several gates involved in the LSTM cell, and these are the core ideas in the LSTM cell. So there's a forget gate, an input gate, and an output gate. But let's focus on just the forget gate for now. So the forget gate controls, which is here, the forget gate controls which information is remembered and which information is forgotten. And it can reset the cell state. So this F here, the forget gate, is computed like shown here. So it's involving two weight matrices. So this weight matrix and this weight matrix. And it's involving the input at time step t and the hidden activation from the previous time step. So we have this hidden activation coming in and the current time step input coming in. And then also a bias unit. And then this one is a logistic sigmoid activation function. And as you know, for the logistic sigmoid activation function, the output is between 0 and 1. So yeah, and what is going on now is we are multiplying this one, which is between 0 and 1, with the previous cell state. And it can technically be 0 and then disable the previous cell state. And if it's a 1, then it will just keep the previous cell state. So with that, it can control whether we use that cell state or not from the previous time step. The input gate. Computing the input gate, which is this one here, is actually very similar to computing the forget gate. So you can see these blocks here look very similar. And also the input gate depends on xt and ht minus 1. The only difference is that we have a set of different weight matrices here compared to the forget gate. But also here we have the logistic sigmoid activation such that the output can be between 0 and 1. The other part here is the input node, which is G here. And please don't ask me why it's called node. I didn't make up this particular notation here. In any case, so this is also, again, computed very similarly to the input gate or the forget gate, except that we have now a 10H activation instead of a sigmoid activation, and this one can return values between -1 and 1. Okay, so previously, so also one more step, sorry, is the element-wise multiplication between the two. So we multiply outputs between 0 and 1 with outputs between -1 and 1, and we use that then using this element-wise addition summation to add it to the cell state, which has been multiplied with 0 or 1 through the forget gate. So the forget gate controls whether the cell state is reset or not, or kept. And then this addition here, you can think of it as updating the cell state by adding a value to it. And this one, for example, doesn't really suffer from the vanishing gradient problem, because for this one, for this addition here, we don't have a multiplication, which is the problem, right? So adding something is not as bad as multiplying something over multiple time steps. So here we don't really have a big vanishing gradient problem for the addition. So just to briefly summarize what we've seen so far. So we have a forget gate, an input node, and an input gate, and we add the result of input node and input gate to the forget gate with this element-wise addition operator. And this one, then you can think of it as a value for updating the stale state. I mentioned there are 3 gates because, like all good things come in 3s. So the 3rd gate is the output gate, and this is for actually updating the values of the hidden layers or hidden units. And computing the output gate is again very similar to computing the input gate and computing the forget gate. By that I mean we again have a logistic sigmoid activation function, and we again use the input at current time step t, and we compute the hidden activation at time step t-1, or we use the hidden activation at time step t-1. The only difference here between the output gate and the input gate is that we use different weight matrices and a different weight vector. So that was talking about this part here. And we are not done yet, so you can see there is something left here. So this part, we have not talked about this part, but we can also briefly cover this part now. So this part is maybe the most important part, because HT, the hidden activation T, is what goes into the next hidden layer, right? So this also goes to the next time step. So if we talk about, or if we're talking about here about this HT here at this position, it would go into the next layer here, right? So this is this purple one here. And it would also go to the next time step. So that would be this green one here. How it is computed is by using the output gate result that we computed on the previous slide, and then applying an element-wise multiplication here with the cell state t, which is coming from here, input to a 10H activation function. And this whole thing is then element-wise multiplied with the output gate. So this is producing the output at the next time step. Why this particular architecture works so well? This is a little bit, too much detail. I think it's also somewhat empirical. We won't talk in too much detail about how LSTM cells work. This was just the walkthrough. We won't talk about the gradients because we unfortunately only have one lecture on RNNs. However, just to mention one second type of cell, while LSTM cells are still very popular today and widely used, there is a related approach called the gated recurrent unit, or GRU cell, which is also very popular nowadays. So it's a little bit newer. It's from 2014 and gets rid of some of the redundancy in LSTM cells. So the researchers analyzed the LSTM cell, what it is doing, and thought, maybe we can get rid of one of the gates, for example. While GRU is a little bit smaller, so here's a short screenshot, it is also more efficient, so there are fewer weight matrices involved, a little bit more efficient at least. However, it's not always performing better than LSTMs. So some research applications show that GRUs are better on some problems, and some show that LSTMs are still better than GRUs on certain problems. So people tend to use both LSTMs and GRUs, and in a practical problem, people usually compare LSTMs and GRUs on a given problem to find out which one to use. So a nice paper on that, an empirical exploration, is this one here, which compares LSTMs and GRUs on different datasets empirically. So how can we use RNNs with LSTMs in PyTorch? As you've seen in the previous slides, LSTM cells are super complicated. There are a lot of things going on, and it would be a little bit painful if we would have to implement it ourselves each time we want to use it. So luckily, PyTorch already provides an implementation for LSTM cells. So to use an RNN with LSTM, what we can do is we can initialize this LSTM cell here. And it requires just the input sequence size and then the size of the hidden activation or the hidden layer. This looks very simple, and really the most complicated part about RNNs is personally preparing the data input to RNNs. So this is a little bit tricky. I prepared a few notebooks for that, or one notebook where I also show you how to do that with a custom CSV file. And I will also show you some resources you may want to read through, some example notebooks. So for that, let's first talk about the many-to-one word RNN. So again, remember the many-to-one architecture is where we have an input sequence and we only need one output, one label. For example, classifying whether a movie review is positive or negative about the movie. And if we think of it in context of the previous slides where we had the many-to-many architecture, you can just think of many-to-one as having the many-to-many architecture, but just canceling these outputs because we don't need them for the many-to-one. So I generated some code examples for you, Jupyter notebooks with RNNs. Unfortunately, at the end of the semester, we don't have that much time anymore to walk through them together. But if you're interested, you can take a look at them. And of course, you don't have to know anything in these code examples for the exam. So I'm not asking you RNN code examples in the exam. It's just optional for you. So in this first notebook, what I implemented here was a very simple RNN without LSTMs, just the normal version, and I'm applying it to an IMDb movie review dataset. So IMDb is a movie database, and there are reviews that for this purpose here were categorized as positive or negative. So the class labels are positive or negative. Unfortunately, this RNN doesn't really work, so it only gets about random guessing performance, like 50% accuracy, and it is probably due to vanishing gradient problems for the sequence data. So in the second notebook, I'm implementing a LSTM RNN with an LSTM cell, and this one is performing much better. So this, I think, when I remember correctly, got like 85% accuracy on the same IMDb movie dataset. And there's also a concept called packing, where I'm packing the sequence, which is making it a little bit more efficient implementation-wise in terms of computational efficiency, but it doesn't affect the accuracy. So you don't really have to pay attention to the packing here. Here the core part really is to have a template for an LSTM. But of course, if in case you need need an RNN for your class project, you don't care about IMDb movie reviews, I guess. So you want to maybe classify your own dataset. So here I also in notebook 3 made an example for using your own CSV data file. Here for this one, I'm again using IMDb, so you can directly compare it to the previous one, but you can also just pretend that this CSV file is just some new dataset, maybe your own dataset. And this one you can ignore for now. We will get back to this shortly. So this is a RNN that generates new text. So we will talk about this in a few moments. And one more thing, because we unfortunately won't have time to cover code examples, and it's maybe hard to look at my code examples, although I try to keep them simple as possible, but there's not much text, so they may be confusing by themselves. I found this very nice repository by Ben Trevitt, and this one is really a great resource, nicely written up Jupyter notebooks with a lot of explanations, and if you really want to use RNNs, I recommend starting here. This is really a very good GitHub repository. This is probably the best you can find right now on the internet in terms of RNNs in PyTorch. So for the many-to-one word RNNs, so I'm calling them word RNN because they operate on the word level. So every input is a word to the network. And so here's a selection of the ones that I would recommend to start with. So there's a simple sentiment analysis, which is just a simple RNN. And there's also an LSTM version. And the coding style is a little bit different from my coding style, but I think the explanations in the notebooks make it really useful for you to read, because in my notebooks, I didn't have that much time to write much comments in there. And again, there are also tutorials for working with your own datasets, and even one for using convolutional networks for sentiment analysis, which is maybe also interesting to you. On the official pytorch.org website, I also found a very nice tutorial on using a character level RNN for classification. So the main difference between a character level RNN and a word RNN is how we process the inputs. So for example, if we have an input, let's say hello world, in a word RNN, what we would do, so word RNNs were what we used before, we would regard each word as an input. So that would be the input at time step t, and this would be the input at time step t+1. And in the character level RNN, the main difference is that now each letter is an input. Let me use a different color here. So the first input, xt, would be the letter H. The second input would be the letter E. And then the third input would be the letter L, and so forth. So in a character level RNN, we process each character at a time. Now we will use that concept of the character level RNN to also generate new text. Or let's just say I'm not showing you how to do that. I have a notebook for that I also uploaded on GitHub. That was the notebook number 4. And I will also provide you resources, but let's at least briefly talk about how that works conceptually. Also think of the RNN, the character RNN for generating new text, as a many-to-many sequence modeling task. So imagine we have a large text corpus and the goal is to generate new text that is similar to the text that it has seen in this corpus. For example, it could be, the network could be reading books and then we ask it to generate new books or to write new books. So assuming we have the text corpus hello world. Of course, this is a very small one. It's you would technically feed a book, a whole book to the network, at least one book. And this is also what I've done in Notebook 4 in the code examples, if you want to look at it. So there I gave it a Charles Dickens book, and the RNN learned how to generate new text that actually makes somewhat sense. I mean, there are some grammar mistakes, a lot of grammar mistakes, but at least it's generating something. Okay, so in the character level RNN, the first input would be the first letter, so H, and then we ask the character level RNN to predict the next word, next letter here, which would be E. And this is also kind of related to self-supervised learning, which we talked about in the very beginning. Because what we are doing here is we are extracting the label actually from our data. So we don't need a human here to provide the label. We don't need a domain expert because the label is already right here in our data set. So we ask the network here to predict the next letter, which would be the E. And then this time step is finished. And for the next time step, we also use the E. So because we move one step further. And then we ask again the network to predict the next letter, which would be the L. So we ask it to predict it, and then we also use it as input again, and then it should predict the next one and so forth. And I'm just seeing, I was pretty lucky that I only have a RNN here with 3 inputs, because if there were 4, it would be pretty weird. But yeah, this is just a coincidence. I didn't plan this. Okay, any case, it's pretty funny, but yeah, ignore this, please. Okay, so this is during training. So during training, we have this many-to-many approach. Also, we have a many-to-many approach when we use the network to generate text. However, I would say it's maybe a little bit more similar to one-to-many, because here what we do is we feed the prediction to the next time step. So what we do is we produce the prediction, and then we feed the prediction to the next time step. And then we make another prediction, and then again we feed it to the next time step. So for example, when we have the letter H. So when we do the text generation, we always have to prime it with one letter, and then we have to let it finish the text, and we hope that it will generate new text. So assuming that it produces some outputs, and the outputs are usually probabilities for each possible letter. So for each letter in the alphabet, you will get a probability. It's just using the softmax function that we used for multilayer perceptrons, but now the output classes are the 20 letters in the alphabet. You can also include punctuation marks, and in practice you would also include a start and end of the sequence character. But let's not get distracted here. Let's just assume we only have letters here. And we would output a probability distribution over the letters here. So we can then sample from that, and we can, for example, say pick the letter with the highest probability at this point. But then it will always generate the same text. So if I say, for example, if by coincidence the highest probability is E, then I will use E here as input and so forth. But then it will always generate the same text if I only pick the letter with the highest probability here. So in practice, what you do is you randomly sample. So use the probabilities as a weight, and then you draw a random sample such that it can generate different text at each time. So for example, the letters like E, A, O may have a relatively high probability because them are words like halo or holla and so forth. So in that case, there's a random probability that I choose any of those, and the softmax probability is the weight for this random sampling. So I may choose A here, and then the network may still predict an L and then complete the sentence or the word halo, for example. But yeah, the idea here is that we take the prediction as the input to the next time step. So the idea is really like that we connect the prediction to the next time step as input, which makes it somewhat more similar to one-to-many, because we only really have one label, really. Actually, we don't really have a label here, so it's feeding itself, essentially. Yeah, so this slide is just, again, a summary of what I just said. So during training for the sequence generation, at each time step we output the probabilities from using the softmax activation and the probabilities for each possible next letter. So if we have 20 letters, there would be 20 probability values, and we sample then from that. And then also during training for the next prediction, we ignore the previous prediction. So we only use that to compute the loss, but we don't use that as the input to the next time step. However, during the inference where we generate new text, there we use the output of the previous time step as input to the next time step. So this is again this connection here where we actually use the output from the previous time step to as input to generate the next letter. Okay, I should also say that this approach also works with word RNNs. So you can also use word RNNs to generate new text where you generate one word at a time. But I think this is less popular. There's a good reason for that, because imagine how many different words there are. So you would have, as the output layer, you would have hundreds of thousands of words in the output, so you have a probability for each word, and that would be pretty huge and probably infeasible. So if you only have maybe a limited number of output words that you want to consider, then it may work. But using, let's say, all words in a dictionary, that would be a little bit prohibitive, which is maybe why the character RNN is more useful in practice. So I have a code example for the character level RNN, so the fourth notebook here, where I gave the RNN a Charles Dickens book from the Project Gutenberg, like the free books website, and then it learned how to generate new text. Again, unfortunately, we only have 15 minutes left, so I can't go to the code example itself, but here are some examples of what it produced. So initially it produced this garbage here, so you can see in the beginning it's really bad, it just outputs random characters, but after 1000 iterations it starts to look relatively good. I was training it a little bit longer, about more than an hour. Unfortunately, it is not great. I mean, it's just one book and it's also not the greatest RNN. I didn't do any hyperparameter tuning as well. So, but still you can see it is learning to generate words. I mean, going from random characters to words like "and the danger folded," down from his, and these are fragments of a sentence that kind of make sense. Of course, the grammar is really broken here, but you can see it's generating some sensible words, which is kind of cool. Yeah, and again, there's another really great set of tutorials by Ben Trevitt. So again, this is a different GitHub repository for sequence-to-sequence modeling. But again, it's really great, and if you're interested, you can take a look at these. There's also one with convolutional networks, and interestingly, there's one called Attention is All You Need, which will be our last topic for today. Okay, one more thing about implementations. Also, I found this nice translation with a sequence-to-sequence network and attention on the PyTorch website. So here they are translating English to French. So again, this is also a many-to-many modeling task, but here you have this delayed output where the network reads the whole sentence first and then it generates the translated sentence. Okay, last topic for today, really now, because we only have like 15 minutes left. Now we are going to talk about the attention mechanisms and transformers. So transformers, you may have heard of them. They are maybe about to be the most popular architecture right now in natural language modeling. Of course, RNNs are still very popular and working very well, but transformers are new and shiny, and a lot of people use them for a lot of sequence generation tasks right now because they generate really good outputs. So let's briefly talk about the mechanism behind it, the attention mechanism, which was first formulated for RNNs actually. Attention mechanism was first originally developed for RNNs for language translation back in 2014. So if you think back of the figure of the many-to-many sequencing modeling that I just showed you, in sequence-to-sequence modeling for language translation in the many-to-many architecture, we have the hidden states, but only in the beginning we receive the inputs. So in blue, that would be the sentence that we want to translate. And then after the network looked at this sentence, it will produce the output. So this is the translated sentence. And of course, all the hidden states are connected. However, that means the sentence that is generated here only depends really on this box here. I mean, this box again depends on previous boxes, previous time steps, but the information is in a way summarized here. So for generating a certain word, it's hard to tell what part of the original sentence the network should pay attention to. So the attention mechanism helps the network to pay attention to certain words at certain time steps or certain translation steps. And as the authors say, it allows a model to automatically soft search for parts of a source sentence. And these parts of the sentence that it should find are the ones that are relevant for predicting the target word in translation. So here at the bottom, this is just a screenshot from their paper. And on the y-axis, they evaluate different RNNs with the so-called blue score. The blue score is just a scoring metric for evaluating how good a translation is. So you can think of a high blue score as good and a low blue score as bad. So you want to have a high blue score when you produce good translations. So they compare 4 things here. The 2 things here at the bottom are regular RNNs. So these RNNs are the traditional RNNs with an encoder and decoder part. So we call this part the encoder part and we call this part the decoder part. And you can see here that they perform very well on short sentences and then the performance declines on long sentences. So you can see there's a limit maybe at here 15 words where it performs well, and then the longer the sentence becomes, the worse the translation becomes. I'm actually not sure if this is the number of words or characters. It may well be the number of characters, but I'm not completely sure. Anyways, the point here is that the translation becomes worse the longer the sentence is. And if the researchers add the attention mechanism, here, this is, let me clean this a little bit here. So if the researchers add the attention mechanism, which they call the search approach, they find that the performance actually improves and it does not degrade. So it only degrades if the sentence length here is longer than the RNN. So the RNN has 30 units, so this is what the 30 here stands for. So only looking at the 50 version here, which is RNN with 50 hidden activations of sequence length of 50, what we can see is that the performance does not decline if we add the attention mechanism. So the attention mechanism is helping the network to perform better in the translation task, because then it doesn't really have to rely only on this part here, but it can look at the whole input. So for each time step here, it can take a look at all the inputs again with a certain weight and look at which are important. So the key part in attention is assign an attention weight to each word to know how much attention the model should pay to each word. So for each word, the network learns the context of the word. Yeah, so here is another screenshot from the paper that summarizes the attention mechanism quite nicely. So what's going on here? So this is the regular, you can think of it as a regular RNN. But the difference now is, instead of getting the input from the previous hidden state and the xt at time step t, so the normal input, xt now looks a little bit different. Xt is now this whole thing here. So what is this thing? This is mainly the attention part. So what's happening here, going through this step by step, is that we have now all the inputs here, x1 to xt. So here note that they are using subscripts where I was using superscripts in the lectures, but it's the same thing. So what's going on here, there's a weighted version of all the inputs. So this is our looking at the whole sentence, our context, instead of just the current input. And also note here, they're using a bidirectional RNN here. Just realize we haven't talked about bidirectional RNNs. You can think of them as RNNs that you run 2 times. So one time you run it forward like before. So you start at the first time step and then you go forward. And then you can think of it as starting at the last item in the sequence and then running it backward, or just simply reversing the sentence and running it forward. So if you would reverse the sentence and run it forward, it would be the same thing as running it from back to the front. And so what that means is there will be 2 hidden activations at each time step, one from the forward and one from the backward pass. And how that is handled in bidirectional RNNs is they are concatenated, so to form one bigger vector. So if you had just one H2 before, let's say hidden layer size 128. Now if you have a forward and a backward pass, now your hidden size is 2 times 128. So you concatenate these 2. So this is just a bidirectional RNN part. This is not unique to attention. What is unique to the attention mechanism here is also that there's a attention weight. And each hidden layer is weighted by this attention weight, and then they are all summed up. So what is provided here as input is still this, let's say 2 times 128 vector, this concatenated vector, but they are all considered here through some attention weight. So there's a weighted version of all the inputs here. That is essentially the attention mechanism. So here I was just redrawing it a little bit, so to make it maybe a little bit more clear. So at each time step, we run the bidirectional RNN, and the bidirectional RNN produces 2 hidden activations, one from the forward pass, I call it F, and one from the backward pass, I call it B. And they are produced for each input in the sequence. And then I have these attention weights that I use for weighting these blocks, and they are summed up to form the context vector. So C is the context vector. And the context vector is then provided to another, or to a more regular RNN, where S is the hidden state of the RNN, which now gets the context vector. In a regular RNN, so if we had a regular RNN like this, then we wouldn't have the context vector, but X here, X1 for example, instead of the context vector. So all that is new is the context vector here at this point, and then the whole way the context vector is computed. And like I showed you in the previous slide, there's the summation term. So the summation term happens here, where we sum up all the weighted hidden activations to form the context vector. So The context vector is a weighted sum of these weighted activations. Now, how are these attention weights computed? So these are the attention weights. So in the paper that proposed this mechanism, they used a neural network to compute the attention weights. So to compute an attention weight, they used the previous hidden state, time step t minus 1, and the current ht time step. So here ht, that would be this one here. This would be ht. And they use a neural network, which, for example, could be a multi-layer perceptron. And this will produce a vector e. And this e is then computed for all the positions here. So you would have each position here, one of these e's. And then these e's here are normalized using the softmax function, such that when you sum them, they sum up to 1. Here's another figure from the paper where they visualized the attention weights. So the task here was translating an English sentence into a French sentence. And for each word, you can see what words it paid attention to. For example, for the word zone, I can't speak French, so I'm not even trying to pronounce it. You can see that it paid attention to two English words here, economic and area. So you can see that for each word, it doesn't only consider the current word, but it also considers some context around it. The attention mechanism was then later, I would say, extracted from the attention mechanism in the RNN. So there is a so-called self-attention mechanism, and there was a very influential paper called Attention is All You Need, which was published in 2017. And this paper, Attention is All You Need, proposes that you only need attention. You don't need the actual RNN, you only need the attention mechanism to get a good performance, essentially. And this kind of forms the backbone of all the transformer papers, if you heard of transformers before. Yeah, we only have 3 minutes left, so can't really talk too much about self-attention, but just to give you a very brief taste. So in the self-attention mechanism, at least in this very, very basic version of it, there are also attention weights. So these W's are not weights learned during backpropagation, but they are here the attention weights that are computed by dot products. So given a current input data point, we compute the dot product of this input with all the other inputs in the input sequence. So we get these dot products and they form our attention weights. So depending on how you learn the word embeddings, so the idea is the more similar the words are, the larger the weight. So the more attention the network will pay to the weight. And then also again, you have like the normalization and the weighted output. Output is computed by the weighted inputs here with this attention. So that is relatively similar to what I've shown you before, but here we don't have an RNN. So that's without an RNN, and the attention weights are created differently. So here they are created with a dot product, and previously we had this neural network that was creating the attention weights. Also, I should say this is only a very basic version of self-attention. In the real attention mechanism, which I would love to talk about, but we don't have time, we would have also 3 weight matrices that are learned via backpropagation. One would be WK, which stands for key. One is for query, and one, I think it's for value. So there are also 3 weight matrices. It's much more complicated than that I'm showing you here. But the idea behind it is that we don't need RNNs. Just using self-attention is already pretty good for working with sequence data. And also the transformer will then consist of multiple of these attention layers, and there's also something called multi-head attention. So multi-head attention is essentially what I'm showing you here, but with 3 weight matrices, and then you have that over multiple channels, like in a convolutional network, and that forms then the multi-head attention block. And this whole thing becomes a transformer block where you also have MLPs, there's a layer norm going on, there's a lot of stuff going on. And I'm not going to ask you about that in the exam, because I know I can only cover this very briefly and would be kind of unfair. But if you're interested in that, there are a lot of implementations here on this PyTorch website, there's a company called Hugging Face, which is implementing a lot of these transformer models from literature, which is pretty cool. And they're all PyTorch implementations here. So lastly, here's a figure from an article I found. It's kind of interesting. So this is listing all the recent transformer models. You maybe have heard of GPT or GPT-2 and BERT models. And you can see it's pretty crazy here in how big they get. So this y-axis is in million parameters. So the recent models even, they are 8 billion parameters big, which is kind of, impressive how big they are. However, also recent research focuses on making well-performing models with fewer parameters. In any case, so transformer models are pretty popular these days. If you want to learn more, I recommend the Hugging Face implementations, and there are also links to the papers on that website. But since this lecture was on RNNs, here is also some optional reading material for you. So that would be chapter 10 from the deep learning book. So here there is also a summary of RNNs. If certain things from this lecture were a little bit unclear, you can also read more about that in that chapter. And with that, I think we also should keep the attention is all you need motto for the final exam. And when it comes to RNNs, I won't ask very tricky questions about RNNs. And with that, I will end the lecture and we'll be back on Thursday talking about autoencoders.